So we're going to look at the applications of exponentials and some of their graphs. We'll start off with the graphing. So the first thing we're going to do is we're going to look at that general exponential equation, which is y equals a b to the x, where a is a constant, b is a constant in the base, and x is your variable. And we're going to graph a parent function of y equals 3 to the x. And the best way to do this is just pick some points and find values for y. So let's call x -2, -1, 0, 1, and 2. When we pop those in, 3 squared is 9, 3 to the first is 3, 3 to 0 is 1, 3 to the -1 is 1/3, and 3 to the -2 is 1/9. Then I'm just going to graph all those. So here's 0, 1, 1, 3, 2, 9, -1, +1/3, and -2, +1/9. So this thing's going to shoot up rather quickly, which is the nature of an exponential. It also, even though it's not drawn in here necessarily, it's also got an asymptote on this line, because there is no number that I can raise a positive number to that will get me a negative number. All right, so there's an asymptote at y equals 0 on that. So in this example, we have to identify our h and k values, and as we can see, our h value is going to be somewhere up here. Our k value is here. We determine by our general equation that h is equal to -5 and k is equal to -1. So moving over 1, 2, 3, 4, 5 to the left and down 1, I insert this fictional translated axis. And then what I'm going to do is I'm going to graph the parent function of y equals 3 to the x using this new translated origin. So I have x and y values. I usually go -2, -1, 0, 1, 2. This gets me 1/9, 1/3, 1, 3, and 9. And graphing from this point here, I go 0 over 1 up, 1 over 3 up, 2 over, total of 9 up, 1 over 1/3 down, and 2 over and 1/9 down. Connect the dots, and that one's done. Let's take a look at the next example. In this case, we need to make sure the coefficient in front of the x is a +1. So I'm going to have to factor here. So I have y equals a negative, or 3 to the -x plus 4. All right, so this x plus 4 right here acts as an h equaling -4. But then this -1 is an x multiplier of -1. So again, I look at that parent function of 3 to the x again. -1 is 1/3, 0, 1, 1, 3, 2, 9, except now I'm going to multiply all my x's by a -1. So this gets me a +1, a 0, a -1, and a -2. And now this column and this column is what I'm going to use to graph from my new origin point, which is -4, 0. So right there is like my new origin. So I'll put a cross set of axes there. And now I'm going to graph from here, +1 and 1/3, which puts me right around here, 0, 1 here, -1, 3, and -2, 9. So now we're going to look at this. Okay, since this is an exponential function and it moves down from left to right, this is called a decay. When it moves up from left to right, it's called a growth. Just an FYI. So now let's look at some of the common application equations that we're going to use. Here is one where n equals n sub o, 1 plus r to the t power. All right, and this is the final amount, n. This is the initial amount. R is the rate, which is usually given in a percentage, and t is the time. Now for the compound interest, once again, this is the final and the initial. R is the rate, typically in a percentage. N is equal to the number of compounds in a year, and T is the number of years. All right, so let's look at a couple examples. So we have a case here where we've got an example of an exponential decay problem because we see that in this case the car is going to depreciate in value, which means it goes down by this exponential of 20% a year. So using our equation n equals n sub o times 1 plus r to the t, we notice we start out with $20,000. And in this case, our rate is a negative 20%. So I'm going to subtract 0.2. And we're going to find out its value at the end of 6 years. So the t value is a 6. Now we're going to pop that into our calculator. And we end up with about $5,242.88. In this next example, we're at a growth rate. So in this case, we're moving up by 7.5%, starting at 22,750 people. Once again, growing by 7.5%, and we're doing that over 10 years. Once again, calculator problem. And this will give us a final answer of 46,888 people. Now, next problem. We have an issue where we're investing money and we're compounding daily, and we want to have $80,000 at the end of our investment for 17 years to put some money in a college fund. So the ending amount in this case, first of all, we're going to use the A equals P times 1 plus R over N to the NT. Okay, we have a final amount of 80,000. We don't know the initial amount, so I'm just going to put that as P. 1 plus our rate is 8.25%, so 0.825. It says it's compounded daily over the course of the year. So there are 365 days in a year, and that's how many compounds we get on this. Raised to the n, which is 365, and we're doing it for 17 years. Once again, it's a calculator problem, and we plug it in. And after grinding all that out, we end up with P equaling $681.62. So we start with that, and after 17 years, we've grown that money to $80,000. Next example is no examples. So answer those questions, and you'll notice that on number 3, I want you to just graph that in your book, and I'll have the answer up on the board tomorrow. Thanks.